Right, are we all ready? So I want to reiterate that, I really like questions. So, and remember that there is no such thing as a stupid question. There are stupid answers, but there is no such thing as silly questions. Don't feel intimidated. Whatever you ask is going to be a great question. At least I will say it's a great question. All right, let's move on. And the next part of my presentation today will be about ultra-cold chemistry, because once you have molecules, at ultra-cold temperatures, one of the things that you can think about is reacting them, and looking at chemical reactions, and that will be ultra-cold chemistry. And June already talked a little about that. I'm going to expand the discussion now. All right. So for chemists, when I give this kind of talks to chemists, they always look puzzled, because chemists, when they normally think about chemistry, when they think about chemical reaction rates, they normally think of reaction rates as going down as you cool your sample of molecules. So they normally think that there should be no chemistry at absolute zero. Okay? So they think that if you start at room temperature, and if your reaction rate, say you have a chemical reaction of an atom and a diatomic molecule, forming another diatomic molecule in an atom, okay? And if you start at room temperature and your reaction rate is up here, they normally think that the reaction rate would quickly go down if you cool your sample of molecules. And so it does for actually most molecular systems. Except that, so it does so, as you cool your sample down to, say, a Kelvin or so. And then, if you continue to cool your sample down to temperatures below 1 Kelvin, then you may see that something strange is happening. Something strange by chemistry standards. You may notice that the reaction rate goes through a minimum, it upturns, and it actually begins to increase as you further cool your sample. Okay? And then in the limit of zero temperature, it will approach a finite and temperature-independent constant. Okay? And the interesting thing is that this constant, this zero temperature limit of the reaction rate, for many reaction systems, it may actually be larger than the room temperature reaction rate. Okay? Now, why is this happening? As surprising as it has been known for many, many years, actually since 1948. Because in 1948, Wigner derived what we call today Wigner's threshold lows. So what Wigner showed, Wigner actually, incidentally, he considered nuclear reactions. He considered reactions of nuclei, but of course all of what he did applies also to atoms and molecules. Okay, so he didn't think about chemistry, he thought about nuclear physics. Okay, but all of the conclusions apply to atoms and molecules. So what he showed is that the probability for elastic scattering, when the elastic scattering cross-section, in the limit of zero collision energy, so when you have two particles colliding very, very slowly, the probability of elastic scattering is energy independent in the limit of zero collision energy. But the probability of the reaction cross-section, is inversely proportional to the collision velocity. Okay? So what I'm showing here is an example of a typical cross-section for a chemical reaction as a function of the collision energy in Kelvin. And as you can see, as you go to very low temperatures, the reaction cross-section just shoots up and it increases as a function that's inversely proportional to the collision velocity, or inversely proportional to the square root of energy. Okay? The rate is, of course, the velocity times the cross-section. You can think of a rate as the velocity times the cross-section. It's a little more complicated than that, but in a nutshell, that's what it is. So the elastic scattering rate at zero temperature is actually going to be zero, because if you have a constant and you multiply it by the velocity, and the velocity vanishes, you're going to get zero. The reaction rate, on the other hand, is going to be a constant, because if you have a function that's inversely proportional to the velocity and multiplied by the velocity, you're going to get a constant. Okay? So that's been known since 1948, the general behavior. What wasn't known is the absolute magnitude of the reaction rates at zero temperature, until some of these calculations, well, back what was it, 2002, this one was a little earlier, 2001. So these are theoretical calculations. The first one was done by Balakrishnan and Dalgarna for the F plus H2 chemical reaction. The F plus H2 chemical reaction has a reaction barrier. So, and the reaction barrier is in the order of, I don't remember exactly, but something like half an electron volts, or something like 4,000 Kelvin or something like that. So if you go to a temperature below the height of the reaction barrier, this reaction must occur by tunneling. Nevertheless, the reaction rate at zero temperature, it was calculated to be 10 to the negative 12 cc's per second. That's a large reaction rate. Okay? If you look at a reaction of an alkali metal atom with an alkali metal diatomic molecule, like sodium plus sodium 2 reaction, this is also a calculation. These people found that the zero temperature reaction rate for these reactions is on the order of 10 to the negative 10 cc's per second. This is a very large reaction rate. What this means is that as many as about 1 million molecules will chemically react per second in an ultra-cold gas. Okay? So if you have 10 million molecules, you're going to lose them all in 10 seconds, okay? Due to chemical reactions. Okay? Now, why are these chemical reactions, in particular, why is this chemical reaction so fast? Okay? Well, that's because it's the nature of alkali metal molecules. You know, when they interact, they tend to form these very stable intermediate reaction complexes. What I'm showing here is the interaction potential between two, say, rubidium-cesium molecules, or between a rubidium-2 molecule and a cesium molecule. And so this is a multidimensional potential energy surface, right? It depends on all the angles between the molecules and the vibrational, coordinate of the molecules. So what I did here, I took the multi-dimensional potential surface and I calculated the minimum of this reaction surface as I brought the molecules together. So basically, what this is the minimum energy path that the molecules would follow, if they were to approach one another. Okay? So as you can see, when two rubidium-cesium molecules come together, they're gonna go down this very steep potential slope. They're going to form this complex, this 4-atom complex that will then lead to the rearrangement of atoms and produce other kinds of molecules, the other kinds of molecules. So this is what this transition complex looks like. You see, you have these two polar molecules, coming together and forming this 4-atom complex that's very stable. Eventually, the molecules have to escape due to the conservation of energy. They have to either go back to the limit of 2 rubidium-cesium molecules, or they will react and then produce a rubidium-2 molecule and a cesium-2 molecule. Okay, that's this complex, and so as you can see, there is no reaction barrier for these reactions. And this chemical reaction, represents a very wide class of chemical reactions that is known in chemistry. We call them insertion chemical reactions. So we call them such because if you have an atom, say like a rubidium atom interacting with a rubidium-cesium molecule, the rubidium atom wants to insert itself in between the two atoms in the rubidium-cesium molecule. As it comes together with the molecule, the reactants that form this very stable complex. Okay? So reactions that have no reaction barrier, they're going to be referred to as insertion chemical reactions. Incidentally, the reactions that have a reaction barrier, a lot of times we call them abstraction chemical reactions. Okay? Now, because there's no reaction barrier, so there's no tunneling, okay? And at the same time, the reactions are accelerated by the Wigner threshold behavior because the reaction cross-section shoots up as you decrease the collision velocity. And therefore, the reaction rate is very, very large. So if you were to react these two species at ultra-cold temperatures, at temperatures very close to zero, the reaction rate would be very, very large. And that's what Junia observes in his experiments. This is, by the way, generic for all alkali metal atoms, alkali metal diatomic molecules. The reaction paths would look like this. I mean, the absolute numbers will be different, but they will all be barrierless. Okay. So, and if the reaction is allowed at ultra-cold temperatures, and by that I mean that the energy of the products must be lower than the energy of the reactants, because obviously rubidium-2 and cesium-2 will react at an ultra-cold temperature, and rubidium-cesium and rubidium system will not react because simply because you won't have enough energy to go from here up here, right? Okay, so if the reaction of alkaline metal dimers is energetically allowed, it will normally be very, very efficient, and that's what observed in the experiments. Okay. So this opens up the prospects for ultra-cold chemistry. So I would argue that this is a new regime of chemistry, a regime of chemistry that people haven't thought about much yet. Okay? And it opens up many, many interesting possibilities, and I've just listed a few of them that I could think of the other day. So one could use this to study controlled chemical reactions. I'm going to give you examples of that in the next few minutes. One can, of course, look at quantum effects in chemistry because most of chemical dynamics is in most of chemical dynamics research, people think of atoms and molecules as classical particles. And a large class of chemical reactions can be described using classical dynamics, not ultra-cold chemical reactions. Because as the experiments of Professor Ye and show, for example, quantum effects are extremely important in the system. Quantum statistics is important. So you can look at the effects of the quantum effects in chemistry. You can look at the effects of quantum statistics in determining chemical reactions. You can use that to look at detailed mechanisms of chemical reactions, and that's something that chemists are very interested in. In particular, you can look at the role of individual raw vibrational energy levels in determining chemical reactivity. To emphasize this, let me just go back to this slide here. You see the energy difference between the ground state of the reagents here and the ground state of the products here is not very large. It's on the order of maybe 50 Kelvin or so. Okay. So what this suggests is that you can, if you have a sample of ultra-cold rubidium cesium atoms, molecules, you could then, of course it's going to be stable because at ultra-cold temperatures, these two molecules cannot go up here. They have to climb 50 Kelvin, of energy to undergo a chemical reaction. However, if you take these molecules and promote them to a raw vibrationally excited state, that is 50 Kelvin above the ground state, you may stimulate the chemical reaction. Now the reaction will all of a sudden become allowed, and it's going to be very, very efficient. So you can think of using microwave dose, because this energy, the excitation energy, well, maybe it's infrared. So you can think of infrared stimulated chemistry. Okay, and this is of course something that chemists cannot do in thermal ensembles of molecules. Okay, and again, this is kind of generic. Many of the alkaline metal diatoms will have the reaction diagrams that in which the reactants and the products are going to be separated by a very small amount of energy. Typically on the order of less or on the order of 100 Kelvin or so. Okay. All right, so we can also look at the effects of quantum statistics and many-body physics on chemical reactions. For example, if you have a Bose-Einstein condensate of molecules, you can look at the effects of Bose enhancement, and how it affects chemical reactions. Or if you have a Fermi-degenerate gas of molecules, you can, the poly-blocking effects will probably prohibit some of the reaction channels, so you can look at the effects of poly-blocking of chemical reactions. You can look at the effects of tunable fine and hyperfine interactions in chemical reactions. Okay, again, this is something that chemists would normally have thought of because most of chemistry happens at room temperature and above, and the collision energy at room temperature, typical collision energy between the molecules, is on the order of 300 Kelvin. Right? This is much greater than the energy of the hyperfine interactions, which is in the sub-Kelvin, well, sub-millikelvin even regime. So at room temperature, chemists just normally ignore the fine and hyperfine structure, except in rare specific cases. Okay. Now in ultra-cold gases, this will be extremely important. And again, I encourage you to read Junier's papers, the experimental papers that demonstrated the effect of the specific hyperfine energy levels on chemical reactivity of potassium rubidium molecules. Okay. Finally, you can look at the effects of external space symmetry on chemical reactions, because at ultra-cold temperatures, you can confine your molecules, by optical lattices in low-dimensional geometries, for example. And as we and others showed in many papers, confining a system in say, a quasi-2D geometry or a quasi-1D geometry is going to affect the reaction rate of ultra-cold particles to a great extent. So, what I normally, when I talk to chemists, I normally tell them that, what this is chemistry that depends on the shape of your chemical vessel, right? So you have chemical reaction rates that will depend on the geometry, on the trapping geometry now. Okay.
One question.
Yes.
What's PCCP?
Physical chemistry, chemical physics.
Okay.
It's a journal. It's probably it's the highest impact journal in physical chemistry. Okay. All right. So let me just demonstrate some of the things that I already mentioned. And one of the most exciting things to chemists at least is the possibility of controlling molecular reactions externally, because this is something they have been thinking for a very, very long time. And to emphasize this, I wanted to draw this book to your attention. This is the book by Moshe Shapiro and Paul Brummer, both of whom are pioneers of the research field of coherent control of molecular dynamics. So they wrote this whole book on quantum control of molecular dynamics. Okay, and this is the quote from Paul Brummer from his talk that he gave in 2007 at DAMO. So what he said back then is that experimental and theoretical studies of the coherent control or quantum control of unimolecular processes have seen spectacular growth over the last 2 decades. So coherent control, quantum control of unimolecular reactions, and a unimolecular reaction is a reaction where you take a single molecule, like a triatomic molecule, and you break it into say, an atom and a diatomic molecule by, say, photodissociation, by shining light on it. Okay? So unimolecular reactions are easy to control. Many experiments have demonstrated the possibility of quantum control of unimolecular reactions. By contrast, coherent control of collisional processes remains a significant challenge. Okay? So it is much, much harder to control molecular collisions than to control the breakup of a single molecule. Why is it? Well, it's because the molecules in a gas, typically in a thermal gas, they're moving randomly. They're moving in all sorts of directions. They're moving with different velocities. And if you apply an electric or magnetic field, let's see, what will an electric or magnetic field that we can generate in a lab do to molecules? Well, it will shift their energy levels by, say, up to a Kelvin, right? The electric fields that we can comfortably generate in a lab, they will shift the molecular energy levels by up to a Kelvin. Okay, in a thermal gas, say in a room temperature gas, these species are moving with an energy of 300 Kelvin, so they don't care much about the shifts that are on the order of 1 Kelvin. If you cool your sample to a temperature of half a Kelvin, all of a sudden this 1 Kelvin energy shifts, they become very important. Okay, so you can think of applying, say, an electric field, and if your kinetic energy of the molecules is low enough, the molecules are then going to be aligned along the direction of the electric field. And for sure, this will affect the way the molecules interact. Again, this has been demonstrated for ultra-cold reactions by Junian. Okay, and in chemistry, they're very interested in looking at the effects of alignment and orientation on intermolecular interactions. There's the whole field of stereodynamics that's quite popular. That has been quite popular over the past 20 years. Okay. Now you could also think of applying another field, like say a magnetic field, and bring the molecules together, for example, through Feshbach resonances. And I trust I don't have to explain to you what a Feshbach resonance is anymore, because you heard these excellent talks today and yesterday. And of course, when you do this, you're going to affect the way the molecules interact, the way the molecules react to a great extent. Okay. All right. So a few examples I wanted to show you include, of course, the work of David Jean and Jun Ye. I don't have to say much about this anymore. Just want to show this graph here that shows that the reaction rate, the measured reaction rate, is a function. Well, this is really an applied electric field. It's a function of the applied electric field. And what this shows is the reaction of molecules confined in a quasi-2D geometry. This curve is for the reaction of molecules in the same vibrational state of the optical lattice potential. As you can see, it goes down as you increase the dipole-dipole interaction strength between the molecules, because it's repulsive. Okay? So if the molecules are in a different vibrational state of the lattice, they will do this as you increase the electric field. If the molecules are in free gas, I believe you get this. I hope that I'm interpreting this graph correctly. All right? Now, what I'm particularly excited about is the possibility to study the effects of electron spin alignment, not the electric dipole alignment, but the electron spin alignment of molecules on chemical reactions. Because when you confine your atoms or molecules in a magnetic trap, what you're doing really, you're aligning their magnetic moments, their electron spins, right? So if you had a diatomic molecule in a doublet sigma state, like calcium H, doublet sigma means, it's the simplest case of molecules that has one unpaired electron, okay? So the projection of the orbital angular momentum of the electron on the interatomic axis is 0, and it has one unpaired electron. Okay, so because it has one unpaired electron, you can magnetically trap it. And calcium H was trapped in the experiments of John Dole back in 1998. This was actually the first molecule that was magnetically trapped, calcium H. Okay, so if you now co-trap it with, say, sodium atoms is a double gas atom. Okay, if you co-trap it in a magnetic trap and then let them interact, the magnetic moments of the atoms and the molecules will be co-aligned. And of course, when you bring, it's like, you probably have seen the interaction energies of the hydrogen molecule, right? There are two curves, one goes up and one is very attractive. The one that goes up is the one that's determined by the exchange interaction, because it's the one that corresponds to the two electron spins of the molecule co-aligned, right? If you flip the orientation of one of the spins, then you're going to experience the interaction described by the lower energy curve. That's much more attractive, because the exchange interaction that's typically repulsive is much weaker when the two magnetic moments of the two particles are anti-aligned. And that's very generic. So if you have an atom and a molecule whose magnetic moments are co-aligned, they will typically interact, they will typically experience significantly repulsive interactions. So they may still undergo a chemical reaction, okay? Except that they will have to climb over a very significant reaction barrier, okay? So normally these kind of atoms and molecules will not want to approach each other to a very short range. Okay? If you, on the other hand, flip the orientation of one of the magnetic moments, like say flip the orientation of the molecular spin, then the atom and the molecule are going to interact through this very attractive interaction potential, the singlet state. Okay? And the reaction on the singlet state is going to be of the insertion type, just like the rubidium-cesium chemical reaction. So if you have a sample of sodium atoms and a sample of calcium H atoms confined in a magnetic trap, it will normally be stable, assuming there is no spin-Zeeman relaxation. That's a separate question. It will normally be chemically stable, except if you were to just then flip the orientation of the spin, and then all of a sudden you would induce this reaction just simply by changing the orientation of the magnetic moment. And there are experiments currently developed that aim to do just that. Okay? Now, where are we in this field of ultra-cold chemistry in 2012? Okay?
One question.
Yes?
When there is this reaction, the gas will be heated up.
Well, it's a very good question. I promise to say that it's a very good question. So it's very good, but it is truly a good question. Yeah, so the question is, when you have atoms and molecules trapped, and then you have a chemical reaction, this will of course release a lot of energy. So the question is, will it lead to the heating of the trap? Well, there are two answers to this question: yes and no. In first order, the first order answer is that it will not lead to heating, because usually these are not very dense samples. So normally when the molecules undergo the chemical reaction, the energy released is so enormous that they will leave the trap so fast that they will not collide with any other atoms, and so they will just be lost without affecting the other atoms or molecules, right? However, when it comes to this kind of traps, magnetic traps, the majority of the atoms and molecules, they're sitting near the bottom of the trap. That's where the density of the sample is the largest. So when you have a chemical reaction, most of the chemical reactions will happen in the region of the trap where the density of the particles is the largest, right? So that where the temperature is the coldest. So a chemical reaction will be removing the coldest particles typically the coldest particles from the trap. And therefore, after the re-equilibration of the energy, you will generally be generating a sample that has a higher temperature, simply because you're removing the coldest particles. Is that satisfying?
Thank
Good. All right, so I just wanted to, I have 5 minutes left, so I wanted to finish by summarizing where ultra-cold chemistry research is in 2012. The experiments have advanced to the point of being able to measure ultra-cold chemical reactions by looking at the trap loss. So you have a sample of potassium rubidium molecules in the experiments of Professor Ye. What they look at the trap loss. They look at how many molecules they lose, per millisecond or whatever time unit they use, and that tells them what the rate of the reaction, because every reaction will expunge the particles from the trap. Okay? There are experiments being developed to probe the effect of magnetic moment alignment using magnetic traps. Jonathan Weinstein at the University of Nevada, Reno, is particularly interested in that, and he's pushing hard to do this kind of measurements. John Dahl at Harvard is also looking at this. Okay? Now, the theory is at the point where there are model theories. Professor Ye mentioned that you can describe this reactions of potassium rubidium molecules with very simple formulas, but these are very model theories. They're very model empirical theories. They need a lot of input from the experiments, and they're based on many approximations. So they describe the experimental observations very well. However, these theories have a limited prediction power. Okay, so there are model theories that fit the experimental data on trap loss developed. Okay, and that's pretty much it. So that's all we have for ultra-cold chemistry in 2012. And the bottom line, so this kind of demonstrates that this field is still in its infancy. Okay. So what are the challenges? What are the challenges that ultra-cold chemistry research has to overcome to become, a really active field of research? Well, first of all, we need to be able to measure the reaction products, not just the trap loss, but we want to be able to look at the reaction products, because that's what chemists do all the time. They not only look at the reagents, they also look at the products, because that allows them to look at the state-to-state reaction cross-sections, reaction probabilities. And the state-to-state reaction probabilities is telling us a lot about mechanisms of chemical reactions. Okay? And it's very hard to do that, because it's very hard to do that in a trap, because when you have a chemical reaction in a trap, the particles that just leave the trap so fast, and the density of particles is so low that it's very hard to detect the departing particles. Okay? So at present, measurements are restricted to alkali metal dimers. Okay? Simply because the most successful method for creating diatomic molecules, ultra-cold diatomic molecules, is based on the photo association, and so we start from ultra-cold atoms, and these are alkali metal dimers. So we need to cool other species, diatomic and polyatomic, to ultra-cold temperatures if we want to enrich the field of ultra-cold chemistry. Because chemistry is not just about alkali metal dimers. In fact, chemists don't like alkali metal dimers. They don't think of them as real molecules. To me they're as good as H2, but they don't like them for some reason. So, and there's a lot to learn from other kinds of molecules. So in order to enrich the field of ultra-cold chemistry, we need to go to other kind of molecules. We need to develop rigorous theory to describe chemical reactions at ultra-cold temperatures. It's very hard. It is very hard because it needs to include the external field effects, the trap and field effects, and it relies on intermolecular interaction potentials that are very hard to calculate. Okay, but this is probably the best time and place to stop. I'm going to tell a little more about this tomorrow, the day after tomorrow, my second lecture the day after tomorrow. I'm going to tell you about this, and I'm also going to tell you about another aspect of ultra-cold molecules, that is the quantum simulation of many-body, condensed matter physics Hamiltonians, and that's what the second part of my lecture will be focusing on the day after tomorrow. Thank you for today.
Are there further questions? Can we see the next
Well, yeah. You want to see on them all? That's the preview of my lecture for tomorrow.